In this topic, we describe how an applied electromotive force, EMF, causes electrons in the atoms of conducting materials to move from one atom to the next, thereby creating electron flow. In recent years, the use of electricity has become an increasingly important and integral part of our daily lives. Not only for those of us who work in the electric power industry, but also for the general public. A knowledge of the basic fundamentals of electricity and its application is increasingly becoming a necessity. In this 4-module program on basic electrical fundamentals, we'll be introducing and studying the general physics, that is, the basic natural laws which govern the application in utilization of electricity. This material will serve as the solid foundation on which to build the more advanced concepts that are dealt with in our many other training programs. In presenting this material, we have tried to limit the application of mathematics and complicated calculations, preferring instead to demonstrate concepts by the use of powerful animated graphics. However, we cannot dispense with calculations altogether, so I encourage you to stick with us. This material does get more and more interesting as we proceed. Now, at this point, I can tell you from experience that somebody always asks the question, so tell me, what is electricity? Well, this same question has been pondered by scientists for hundreds, if not thousands of years. One of the most popular theories advanced is that of electron flow. In this arrangement shown here, we have an electrical device, perhaps an electrical heater or an electric light bulb, a measuring instrument or other machine. This device, which does work for us, is generally known as the electrical load. 2 conductors are connected to the load at one end and to a voltage source at the other. When the circuit is energized, the voltage provides an electromotive force known as EMF, and this, if it is of sufficient magnitude, it creates an upset in the balance of the atomic structure of the conductor material. Now, let's take a closer look at this literally. You will remember from your high school physics that all materials are made of molecules, and these in turn consist of atoms, which are made of protons, neutrons, and electrons. If we have a powerful enough microscope able to magnify by millions of times, we would be able to observe the atomic structure of the conductors. We would see a large number of atoms, each of which has its nucleus surrounded by electrons orbiting the nucleus, somewhat resembling a mini solar system. Applying an EMF across the conductor creates a difference in potential, and if this is large enough, some electrons will be forced out of orbit to migrate and take up residence in neighboring atoms, consequently forcing other electrons out of their particular orbits. This jumping of electrons from atom to atom forms an electron flow in the direction of the applied EMF. Note that the electron flow continues all the way through the customer's load, thus doing some work, and then flows back through the return conductor to the voltage source. The actual number of electrons that are flowing through the circuit depends upon 2 factors. The magnitude of applied voltage, so increasing EMF will increase the number of electrons flowing. The resistance to flow offered by the atomic structure of the materials involved. For example, conductors allow the free movement of a large number of electrons, thus providing a relatively low resistance to the flow of electrons. Conversely, other materials, particularly insulating materials, have very few free electrons, and a much higher voltage is required to overcome this resistance to forcing electrons out of orbit.